right, so section 4, we combine a little bit of info from what we've done previously to acid-base chemistry. Again, 2 examples. One involved math, the other is just concept with an equation. Important point here, in a neutralization reaction, acid and base react together, give us water and salt. Now, typically when we think salt, we think sodium chloride, table salt. However, in chemistry, a salt is an ionic substance. Okay? So when we say salt, it's like a generic term. A major...
Salt's not an acid or a base?
Correct. Now,
it's a solid.
Yeah. At the end of the chapter, or at the end of section 4 here, this section, we'll talk, they kind of have a unique set of properties, and we'll see that. Yeah. The other thing I want to emphasize is this. A neutralization reaction. It has a one-sided arrow, a standard chemical reaction. We're not dealing in this part with equilibrium. Okay? So, titration. This is our lab, and like I said, it's a pretty fun lab. Our titration is this. I want to bring up really this point down here at the bottom. It says equivalence point. Equivalence point equal, you get equal number of moles of acid. That's A+. And that's equal to your moles of base, which is OH-. So, moles of acid and base are equal at the equivalence point, okay? And that's important as we go through this. Now, I just introduced you to our graphs, but if we were titrating, so we're adding drop by drop, in this case a base, when we get to the equivalence point, all of a sudden we had a really low pH and you get a dramatic uptake in the pH. And that's because equal moles of acid and base have been achieved, and now you have base in your solution.
Do we have to draw those?
You will not have to draw it. Like I said, AP chemistry, we spent a couple of days talking about building these graphs. I just want to introduce them to you. Okay. Same thing here on this graph. Now, depending on the substance that you have, you saw there is another indicator, and we'll talk about this on the next slide, will determine what you need to use to be able to see that change, all right? So in chemistry, there's a bunch of different indicators. We're gonna use this phenolphthalein, where it's gonna go from clear and colorless to, at the equivalence point, we're gonna get this nice faint pink solution. Again, variety of other indicators that you could use. The big thing is, where does that big uptake in pH cross, okay? Now, here's our example problem, our steps to do our example problem. We combine chapter 15 stuff on solutions, which I'm gonna give you the formula, and stuff on chapter 12, stoichiometry, and we put it into an acid-base equation. So, here we go on this. We have, or we want to know, what is the molarity of HCOOH, acetic acid, aka vinegar. If we have 25 milliliters of this solution, and it's titrated by 18.28 milliliters of 0.1 molar NaOH. So we're going to start out with what we first have, and we have multiple parts of this guy right here. We have 18.28 milliliters of 0.1 molar. Now we backtrack to chapter 15, and we use this formula quite a bit. I said big M. Does anybody remember what big M, the formula was? We had what on top? Moles, very good. All divided by liters. Very good. Liters, specifically liters of that solution. So now, that part that I underlined there, we can start filling in the gaps. We have 0.1 big M, or 0.1 molar, and so I put in 0.100 big M. This is equal to our moles. Do we know, or does the problem even list anything about moles? No. So we don't know our moles. And remember, this is for NaOH. So I'm going to put that just to remind us. Now, it's divided by liters. Is 18.28 in liters?
So you gotta multiply by 100, 1,000.
Divide by 1,000. You're on the right track. Divide by 1,000. And so if you take 18.28 divided by 1,000, you end up with 0.01828 liters. Now, we cross what? Very good. We cross multiply. So if you were to plug 0.1 times 0.01828, you would end up with this. And I'm going to write it below. 0.001828 moles of NaOH. All right. Well, that's great, but we need to get it over to our acetic acid. So here's where that chapter 12, that stoichiometry comes into play. We say times, we draw our line, we got to cancel out mole of our NaOH, and on top we want to get to where we're going, which is mole HCOOH, and mole over mole. Anybody remember where we get our numbers for that?
The problem.
Yep. So right here, what are actually both of these?
0.
Not 0, we assume it's 1. Both of these have coefficients of 1. Now, the reason we do this, it's not always going to be this case. This means that we still get 0.001828 moles, but we have shown that we've converted to HCOOH. Great. Now we can finally get to our problem, which is we want to know the molarity. So we want to know big M of acetic acid. On top, we already know moles, which is 0.001828 moles of HCOOH. We divide it by liters of this stuff, which is not 25, but what would we have to do?
Divide by 1,000.
Very good. Divide by 1,000 milliliters, which gets us 0.025 liters. And so when we plug this into our calculator, what we get is this. Typically, we show this in either 2 or 3 non-zero numbers. We're going to use actually 3 here. We are going to get 0.0731.
Interruption. For our next year seniors, if you apply for the workspace program, please report to the library this time for a brief meeting with the guidance counselor. Again, our next year seniors, if you apply for the workspace program, please report to the library this time. Thank you.
So 0.0731 big M for molarity, and then we always put our substance HCOOH, and that is our answer. All right, questions? Does anybody still need this? Okay. All right, we got one more example. There's no math in this next example. So, salts. Kaylee, I think you talked about stuff with salts. When salts dissolve, remember solid, like a solid table salt, something unique happens is we identify what could be a weak acid or potentially a weak acid or weak base. Okay? In that case, we can start to underline or understand this idea of what happens here. Now, again, a salt has to involve your weak acid or weak base. So the hardest part is going to be determining, well, what is a weak acid or weak base? Then we introduce that equilibrium because it's weak. Okay, so let's try an example here. We have ammonium chloride, which is a solid. So ammonium chloride is NH4 NH4Cl. Now, ammonium splits apart from chloride. And so if it's dissolved in water, that's what we're showing here, we get two things. Number one, NH4 with a positive charge. And again, AQ, it's dissolved in water, plus Cl minus, AQ dissolved in water. Now, this is where I'm going to hear from you. Is one of these two things is either a weak acid or weak base that's going to go through that process or go through a similar type of situation we saw in that example? Of these two things, anybody have an idea what is either our weak acid or weak base? Yes, very good. Now, I'm going to get to explaining why Cl minus is not, but I'm going to pick apart NH4 with a positive charge, right? It combines with water, just like we saw in the last example. Now, NH4 plus, take a guess here, is that an acid or a base? Acid, it's a weak acid, so what happens to one of its H's? Yep, gives it away, and it forms this. Again, equilibrium, H3O plus, which is AQ, and we get our NH3. All right, so that would be that would really be our answer, what the equation I wrote in green. Here's why we don't play with Cl. If Cl, we have to accept another H. If Cl accepts another H, and we have HCl, is HCl a strong acid?
No. Yes.
It is. This process that I wrote in green cannot happen with a strong acid or a strong base. It has to involve either the weak acid or weak base.
Can it not work because there's only one H?
So,
Or does it not matter how many H's?
the real reason why is this. HCl, because it's strong, it actually breaks completely into H plus and Cl minus. Because it completely breaks apart and we don't have this back and forth part, that's the real reason why. Because all of the H's would split apart from all of the Cl's in a strong acid or a strong base problem. And so therefore, there's no opportunity to do this equilibrium. So it starts to get really in depth with chemistry there, but because it's strong. That's a good question. All right, any other questions? Anybody still need this? Okay, so our last thing is this, buffers. Really, I should have probably highlighted or boxed in. This point number 1 and both points A and B and below that are really important. Buffers resist dramatic changes in pH. The reason why is this. They have a weak acid and its conjugate base, or a weak base and its conjugate acid. You have to have these criteria. So if you just have a weak acid, you don't have a buffer. If you just have a weak base, you don't have a buffer. Have to have some of each. If you have some of each, you allow either an acid or a base to be absorbed by those things. That's that resisting of that pH or change in pH, because you can absorb either an acid or base that gets dissolved. Last thing here, buffer capacity. How you form a good buffer capacity is one of two ways. One, you have pretty large quantities of weak acid and its conjugate base. And then two, as close as you can get them to being equal, right? So if you have 1 part weak acid, you should have 1 part conjugate base to make it as strong as buffer as possible. Last example here is this. Your blood has a pH about 7.4, which is good. It is a buffer, which is really, really good, because when your body gets sick, those changes in your bloodstream, because there's change, or because you have a buffer, it's going to resist that change.
Against your seniors that are in the workforce, work study, workforce, work study, please come to the library. Thank you.
So you have your pH or your blood, which is a buffer. It's going to resist change, which is good because when you get sick or when you eat something you shouldn't, it's going to resist that change. And if you have pH in your bloodstream that gets out of whack, vital organs start shutting down and things are not good. All right, questions?
Oh, no. Where'd my garbage can go? Where's my garbage?